So welcome back, everyone. I've uploaded a lot of things to our Canvas website. All of the lectures are up to date, and I uploaded some guidance as to the next midterm, which is on Thursday. Some of the topics. Um, so I think that there should not be any surprise to most of you or all of you what's going to be on the exam. So probably the last thing that we'll cover, and it's still going to be kinetics. Probably if I don't finish it today, on Wednesday. So whatever I cover about kinetics will be on the midterm on Thursday. Whatever I cover on Wednesday, up to that. So kinetics will be the final topic that will be on the midterm. So everything we've done, finishing up kinetics. So I think that's pretty specific in terms of what you should focus on. Okay, and then I hopefully I've been pretty clear on and the homework has been pretty illustrative of the concepts. The homework actually has been quite straightforward in my opinion. I could have given you, in the past I've given quizzes which were a little bit more difficult or more challenging. That's the word I like to use. But I think the homeworks are pretty straightforward. So if you understood the lectures and the homeworks, I think you should have really no problem, even with the time constraint on the exam, to do well. Okay. So my only encouragement for you is to, don't get, just don't make a mountain out of a molehill. Just make sure you know what just you all. I'm very confident you all have the tools to do it. So just don't shoot yourselves in the foot. Okay, so let's continue. So I do want to go back and just correct a few things. So actually, just one thing really. So we looked at the chemical reaction, reversible chemical reaction for ideal gas system. So everything in the system is an ideal gas, and we came to the conclusion that the equilibrium constant, which arises because of this constraint that the Gibbs free energy, the total Gibbs free energy of the system as a function of this extent of reaction has to be at a minimum when you have equilibrium. And we know that G is given by this expression. And when we make use of these two concepts, in addition to the fact that for an ideal gas, the chemical potential is some reference state chemical potential plus RT log of this ratio of pressures, we obtain this chemical, the equilibrium constant, which is given by this expression, which for the case of an ideal gas, okay, when we have a mixture of ideal gases, is really this product of the ratios of the partial pressures of each gas divided by this reference state pressure that you use, all raised to the stoichiometric coefficient of the species in the chemical equation, in the balanced equation. And in this case, I have a product because I haven't used my intuition to say what the SIGN, the signs of the stoichiometric coefficients are. But if I were to use my intuition and follow the convention that we have chosen, which is products have negative and reactants, sorry, products have positive and reactants have negative values of stoichiometric coefficients, we can just rewrite that equilibrium constant in terms of the magnitudes of the stoichiometric coefficients, and we then just put the partial pressures of our products in the denominator because we know their stoichiometric coefficients are negative. Okay, so that's all pretty straightforward. I mean, that's not that difficult. That's just a review. And then we found also that, let's see, where's that expression? Delta G, this thing that we defined, which was the difference in the chemical potentials at standard state or reference state for all of the species, is equal to minus RT log of the equilibrium constant. And again, I want to emphasize here that this delta G is the delta G if you were to take pure species and just take their differences in terms of their molar Gibbs free energies. Okay, so this is not the delta G of the reaction as we've written it. So this delta G that I've underlined in red is not for this reaction. at temperature and pressure. Okay, so this is an at. Okay, so for the chemical reaction that I wrote in red, okay, this delta G superscript 0 with a subscript reaction at a particular temperature T is not the same as what we're looking at in terms of delta G of the reaction, which is at constant temperature and pressure. And that pressure is something else. So this delta G with the superscript 0, of course, is at your reference pressure, whatever that is, that you take it to be, okay, or whatever the reference state is that you've chosen for your individual species when you define the chemical potential, okay? So we see that delta G naught reaction, superscript 0 is equal to minus RT log K equilibrium. We noted that K equilibrium is dimensionless. No matter how you write it, it's always dimensionless. No matter, even if you start with obtaining equilibrium constants using rate laws. So perhaps maybe that's how you were introduced to chemical equilibrium earlier on, through rate laws, okay? Even if you write it that way, those equilibrium constants, they have to be, if you're going to use anything that relates an equilibrium constant to a delta G, okay, it has to be written in a way that it's dimensionless. It has to be dimensionless, because we saw by combining the first and second laws of thermodynamics, okay, because we had to do that once we understood what those first and second laws were. Once we combined them in this very powerful inequality, we obtained, through going through many steps, a criterion that allows us to come at this result. And that result was dg d epsilon is equal to 0. Okay, so this expression, okay, is it's fundamental. There is no way that the equilibrium constant can have dimensions. Okay, it just cannot, unless you're talking about some equilibrium constant that is totally not the same as what we're talking about here, or in any physical chemical system, okay, or biophysical, whatever system you're talking about, okay, electrochemical, we're talking about batteries, what have you, okay? And so I want you to sort of just keep that in mind. I know that the way chemistry is taught is that, well, sometimes these equilibrium constants have units. And next semester in Chem 444, we're going to do the same kind of hand-waving kind of stuff. You'll see equilibrium constants that we arrive at through kinetics, through kinetic analyses that have constants. But in reality, there's a trick. And there are some assumptions that we will get to when we deal with kinetics. Okay? But what I want to keep, for you to keep in mind, is that this law, the equilibrium constant, is dimensionless. All right. The other thing is, and this is where, so let me just go back. So here, let me just right here, remember this was the example I used to indicate that some of you may have seen equilibrium constants with units. Well, there is some trick here. Okay, so we'll get to that later. The other thing is this delta G naught, the final thing I want to, at a particular temperature T, that would be the same as the temperature of the reaction that we're interested in. Remember, we said that this is just, in the case of A, B, C, D, mu A naught plus mu B plus mu C naught plus mu D naught at T. Okay, and if we were to use the signs, this would just be then mu C. We can use the absolute signs of the stoichiometric coefficients plus mu D. And then we would have minus mu A minus mu B. Okay, so that's where that delta notation becomes more obvious, because we're taking the difference between what is ostensibly the products minus what is the reactants. Okay, so the reactants all have negative signs and the products all have positive signs when we introduce this, when we write it with absolute values for the stoichiometric coefficients. And I think, Sheldon, you were the one who said that actually this delta G has to be a molar property, and you're totally right. I don't know what I was thinking when I was talking last Friday. Maybe I was thinking about my bike ride over the weekend, but that's totally right. We see here that the chemical potential is a molar property. It's a partial molar property. It's if you have a mixture, but for the pure species, it's just the Gibbs free energy over N. So it has to be a per mole property. So this delta G naught over reaction is per mole, and on the right hand side, right, R is just joules per mole K, and when we multiply that by T, we just get joules per mole. So here we also get energy per mole or per amount. So these are molar entities. So I think it was Sheldon who said it was a molar property, and you're absolutely right. Correct me if I'm wrong if someone else said it, but I think that was the voice I heard. Okay, so this delta G is really superscript 0 is actually a molar Gibbs free energy, as then would have to be on the right hand side. RT log K has to be per mole. Okay, any questions or comments? Okay, then I'm going to move on. Anything else I want to say for the moment? Okay, let me just say this now. So we have this expression, delta G naught reaction is equal to minus RT natural log K equilibrium of T. Oop, I don't want that there. Okay. If you're given values of mu sub I naught at a particular temperature T, okay, you're given, let's say in a problem, if you're given values of mu sub I naught T, okay, hint, that was a hint maybe. If you're given values of mu sub I, and I is just a species in the system, would you be able to calculate is that something that you could do if you were given mu sub I superscript 0 at the temperature of interest for all of the species? I think so, right?
Yeah, you should, with the chemical equation.
Let's see. I guess it's this one. Yeah, the chemical, yeah, right. Once you had the chemical equation with the stoichiometric coefficients.
Yeah.
Yeah, that's exactly right. Okay, so you should be able to use this thing that I just boxed to be able to get delta G superscript 0 reaction. Okay, given this. All right, I think that's pretty obvious. So let's move on. Okay, last call. Any questions, comments? Because now I just want to look at the temperature dependence of T, because I've written K equilibrium as something that has dependence on temperature. Okay, so we're going to write, we're going to look at the temperature dependence of T. Because oftentimes you may want to know what, you know, a reaction, you may have a particular, at equilibrium for a particular reaction, right? This K equilibrium may be such that if we take a look at this K equilibrium in terms of an ideal gas, remember it was PA over PA naught. That should be on the bottom. Let me do this. The reactants, PC over PC naught, the mu C, PD over PD naught, the mu D, all over the reactants. Okay, so if you're at a particular temperature, right, this K equilibrium will be given by the ratios of what you have. The partial pressures are just a proxy in the case of an ideal gas for a concentration, because we know that P sub A is just NA RT over V. if you have a particular volume in the system, right? So that's that total volume. And we can write NA as the mole fraction times the total number of moles times RT over V. Okay, and so it's some fraction of a concentration. We can say, all right, well, we have some total concentration. We have a total number of moles of species in a particular volume, moles per unit volume. And then if we take some fraction of that, that'll give us what the concentration of A is. So we can formulate this in terms of concentrations too. Okay, so if you think about these ratios of pressures, these partial pressures in the expression for equilibrium constant, you can think about them as concentrations as well. Okay, and so if at a particular temperature, let's say, the thermodynamics and nature will define at a particular temperature and pressure what the concentrations at equilibrium will be. We won't have any choice. Okay, we won't have any choice what those the concentrations will be. But let's say we want to increase any one of those concentrations, or perhaps a couple of those concentrations. But in fact, let's say the product C, okay, is some blockbuster chemical compound that's going to be worth mega bucks for your company if you decide to work for a company, or you're working for a company, or you yourself have developed it, right? You want that concentration to be as high as possible. So you may want to figure out if this equilibrium constant changes with the function of temperature and what that value would be at a different temperature. So let's say, again, this will all be, I'm just hand waving it. We have to be a little bit more detailed, but this is motivating why we want to look at the temperature dependence. If you want to raise the concentration of C, because that's something that's very valuable to you, you may want to figure out perhaps there's another temperature at which you can run the chemical reaction that would allow you to increase that concentration. Okay, and then it becomes just a balancing act of the economics. In a very simple way to think about this is, well, if I raise the temperature, well, then obviously I'm going to need some energy source to raise the temperature. So that's going to cost me, right? And so this is where there's a very cool interplay between economics and science here in terms of developing a process for making something that's useful to society, right? And in fact, it's something that one has to think about, and if you're one of these people who's an entrepreneur who makes something, and sometimes people forget that it costs something to make something, and if the price is of something that we don't like, then the person making that they also have to eat and have a roof over their head. So anyway, this is an example of getting you to think about economics as well as making things scientifically. Okay, it's a whole big picture. It's all interconnected. Okay, so the temperature dependence then really is something that allows us to see, all right, well, what's going to happen with the amounts that we can have in the system in a very specific case of where one of the products is of value to us. And I think it's kind of obvious that we wouldn't do something unless there's value in it. So the temperature dependence we're going to think about is, let's use this expression for the relationship between, well, the equilibrium constant and delta G naught. Okay, so we have that expression. We can isolate natural log the equilibrium of T, and that's just equal to minus 1 over RT delta G superscript 0 reaction at a particular T. And so this holds at some T, okay? We don't know what that temperature is. It's just something we have at some temperature. So if you want to look at the variation of log KT with T. So let's consider the variation of the equilibrium constant, and we'll just keep the log of K equilibrium, that's fine, as a function of temperature, okay? And so for that, we're going to take the derivative with respect to T. Oh, that's not time. It's big T of natural log okay, equilibrium of T. Okay, so that's the left-hand side of this expression. And we're going to keep the pressure constant. Okay, so we can take that if we want to do it that way. And then we're going to do the same on this side, d dt of whatever's on this side, which is minus 1 over RT times delta G naught of reaction at a particular T. And of course, this is going to be at constant pressure as well. Okay, so we'll do this at constant pressure. Okay, so what we want is the left-hand side, but we have a lot more information on the right-hand side. And so let's see what we can find here. Okay. So we can take the R minus 1 over R outside because that's just a constant. So that's just going to be minus 1 over R d dt of 1 over T times delta G superscript 0 reaction of T at constant pressure. So now we have a product here. This is a product. And both of those guys are a function of T. Okay. 1 over T is a function of T, and so is the delta G, as we noted through the temperature dependence in the parentheses. So we're going to have to use one of our calculus rules to take that derivative. Okay, and that's just, I think, the chain rule that we'll use. So we bring the 1 over R along. We can't neglect it. And now we're going to use the chain rule to take the derivative of that product with respect to temperature, because that's what we're interested in. And the pressure is constant here. So what I'm going to do first is keep the 1 over T constant and take the derivative of the delta G. So that just gives me a term like this. 1 over T is constant. I'm going to take d delta G dt at constant P. Okay. Now I keep the delta G term constant and I take the derivative of 1 over T with respect to T. And that 1 over T derivative is just going to be minus 1 over T squared, because that's just 1 over x, and the derivative of 1 over x with respect to x is minus 1 over x squared. So that just becomes 1 over T squared, and there's a minus, times delta G naught of reaction at T. And that's all at constant pressure. And so let me just remind you that this is the temperature derivative of natural log K equilibrium of T. Okay, that's just at constant pressure, bringing this guy down. So this is what we have for our expression now. We have two terms for the temperature derivative of log K at constant pressure. Okay, everyone good so far? Okay. So what I want to do now is take a look at something here. I have here a d dt of a delta G. Okay, let's generalize here. Okay, let's do something in generalization. So I have delta G superscript 0 reaction, but that's just a delta G. Okay, so if I wanted to just generalize this, really this is the temperature dependence d dt of a delta G. Okay, it's the temperature derivative of a delta G. In general, I just, the superscript and the subscript are just bells and whistles to be very specific, but in the general sense, this is just a delta G. Okay, and we can think about this let's see, in terms of the total differential. So d of delta G, okay, is going to be something. Okay, we can say that that's delta G prime times dt. Okay, and this delta G prime would be the derivative. That's just the derivative of delta G. Just like dx dt is equal to x prime, then we know that dx is just equal to x prime dt. Okay, just keep that in mind. Right. That's just something you may remember from calculus. So what I'm going to look at is this guy, d delta G. Okay. Recall that delta G is just equal to G final minus G initial. That's what a delta is. Okay, and since G is a state function, all we have to worry about is final minus initial. So D of delta G is just equal to D of G final minus G initial, which is just equal to DG final minus DG initial. Okay. Any questions so far? So I'm actually interested in this D delta G for the moment. And that's all I'm doing here. So therefore D delta G is equal to, but we know what DG is. Remember from our very general discussion earlier on, we derived this DG is equal to VDP minus SDT. Okay? Recall. So D delta G is equal to DG final minus DG initial, but DG final is just V final DP. Let's see, minus S final DT. And then you have the terms that are the initial, which is V initial DP minus S initial DT. Okay. And since we have DPs and DTs that don't matter whether they're initial or final, okay, we can lump everything that has a DP together and everything that has a DT together. So what we find with the DP terms is V final minus V initial times DP minus what we're going to have here is an S final minus S initial times DT. Okay, so that's what this D delta G turns out to be. Okay. But V final minus V initial, that's just delta V. So we have DP. And then S final minus S initial is just delta S. Okay. So D delta G is just delta V times dP minus delta S times dt. So any questions? So now if P is equal to a constant, since we're interested in this stuff at constant pressure, dP is equal to 0. So therefore D delta G is equal to minus delta S times dt. Okay. And so therefore we have D delta G dt, if we bring the dt over, is equal to minus delta S at constant pressure. Wow. All right. That's actually useful. Any questions how we got here? Okay, so D of delta G dt at constant P is equal to minus delta S. We can use this expression now because we needed it right here. There's that D delta G of reaction, dt at constant P. Okay. So let's do that. Let's go back and then write that there. So d dt of natural log K equilibrium of T at constant pressure is equal to minus 1 over R times, let's go back, 1 over T times is d delta G dt. So that's just going to be 1 over T times minus delta S of this reaction. Since that's for delta G, we have to use this this expression for the entropy change of the reaction at this reference state. Okay, and then the rest is just minus 1 over T squared times delta G superscript 0 reaction at T. And there we have it. We're getting there. That's pretty good. Okay, that's pretty good. So let me sort of clean this up. This is just going to be 1 over R times, here we have minus delta S over T. And then here we have delta G over T squared. Okay. Any questions so far? All right. But recall, so now we can recall because we have all these tools that we've developed so far. Delta G is equal to delta H minus T delta S. Remember G is just, G was defined as H minus TS. Another recall, right? So therefore, delta G is just delta H minus T delta S at constant temperature. And of course, this chemical reaction is going to be, this derivative is an instantaneous derivative at a particular temperature. And so the right-hand side is okay. We can think about this as constant temperature. Okay. So we can substitute this guy here. Okay. And so that gives us dt of natural log the equilibrium of T at constant pressure is equal to minus 1 over R minus delta S naught of reaction at T over T. And this delta G all over T squared, okay? But delta G naught is just going to be delta H naught of reaction of T. And then we have here minus T delta S naught of reaction of T. Okay, and what we find is that, let's take a look at this term. This is a minus delta S naught reaction of T over T, okay? And then the term that arises from the delta S in that second term was just going to be a positive, right? Because we have a negative sign out here. And that negative sign is going to multiply this negative sign. Okay, so that's going to give us a positive, which I've denoted here. And this T is going to cancel one of these T's. And so what we're left with is a delta S reaction over T. And you see here that any of the entropy contributions for this derivative vanish because the two terms annihilate. And that's very nice because then all we're left with for the temperature dependence of natural log K equilibrium at constant pressure is minus 1 over R times whatever's in the parentheses, which is delta H naught of reaction at T over T squared. And that's the only thing that survives. Then we just make this a little clean. We just say that the two negatives give you a positive. And so then that's just delta H naught of reaction over RT squared. There you have it. So that's the temperature dependence. That's the temperature derivative of the equilibrium constant at constant pressure. And it's related directly to the enthalpy of reaction at standard state, the reference state, and the temperature of interest divided by RT squared. Okay? And so we know that delta H naught of reaction at a particular temperature is easy to compute once you have the enthalpies of formation. Okay, so the enthalpies of formation may be given at P naught 1 bar and T equals 298.15 K, but from our discussion of thermochemistry, you know that you can compute delta H superscript 0 of reaction at any temperature using the specific heats of the various components. And all of that information would be given to you if you had a problem, or if you're working out in industry or any other environment, you would have to obtain that information and that data somewhere, whether it's through your own experiment or you would look it up somewhere. Okay, so we see here that the temperature dependence of the equilibrium constant is actually quite easily determinable from things such as entropies of formation, incredibly, okay, of species in a chemical reaction. So this is the general form, okay? So this is very general. So this is the general form of the temperature dependence of the equilibrium constant, right? We can say that if delta H naught, a reaction of T, is weakly dependent on temperature, that means that's another way or a euphemism for saying that don't worry about delta H naught and its temperature dependence, just take it as a constant. Okay, so maybe you're interested in, and in practice, you know, you can do that perhaps as a first pass if you're trying to compute temperature differences for K equilibrium. Let's say on back of the napkin type of a calculation. You can just let delta H be a constant at a particular temperature and compute what the equilibrium constant would be at a different temperature. And that would be rather easy. The way we would do it then is as follows. Okay, so if delta H reaction is weakly dependent on temperature, we consider it a constant. So therefore we have d dt of natural log K equilibrium is going to be delta H reaction. I'm going to keep that T in there for the delta H of reaction, but you know, I already said that it's weakly dependent, but I just keep it in there. And then we're going to have, let's see, 1 over T squared. So this guy then effectively becomes a constant because we said delta H is, it's okay to take it as a constant. So D natural log K equilibrium, oh yeah, this is a constant pressure, is equal to delta H naught reaction over R times 1 over T squared dt. Okay. And we know that the equilibrium constant is a state function. Okay, the equilibrium constant, it doesn't matter how you go from temperature 1 to temperature 2, the equilibrium constant is going to be wherever it is at those two temperatures. That's one way to think about it. I mean, intuitively. The other way is to just, you know, if you need to resort to something that is absolute, right? Let's see, where did I write it? Right here. Log of K equilibrium is equal to delta G. It's of G, and G we know is a state function, right? R is a constant, T is a state function, then it has to be that log K equilibrium is a state function. It has to be because it's equal to state functions. It can't be there can't be anything else. And so we can take this as, now we integrate from T1 to T2, whatever the two temperatures that you're interested in are. Okay, so this just becomes the integral from T1 to T2 of natural log K equilibrium of T. Okay, oh sorry, it's the D of that. And that's going to be equal to delta H naught reaction over R. Now we have the integral from T1 to T2 of 1 over T squared dt. Okay, but since this guy is a state function, the integral of d state function is just going to be the difference in the state function at the two endpoints. So that's just K equilibrium at T2 minus log K equilibrium at T1. And that is going to equal delta H naught of reaction over R. And then this guy, this is the integral of 1 over T squared. That's just going to be minus 1 over T. So it's going to be minus 1 over T2 minus 1 over T1. Okay. The integral of 1 over T squared is minus 1 over T. So all I have here is minus 1 over T2 minus 1 over T1. Okay. So that's just equal to delta H naught of reaction. T1 now R. So this is just 1 over T1 minus 1 over T2. So natural log, and now we can write the difference of natural logs as a product, as a ratio. And that's equal to this, where delta H okay, so where we assume that delta H naught reaction is weakly dependent on T, we get this result for the ratio of the two equilibrium constants at two different temperatures. Okay, log K equilibrium at T2 over K equilibrium at T1 is equal to delta H reaction over R, 1 over T1 minus 1 over T2. Okay. And if you want to keep this in terms of another form, this is just we bring the minus sign out. And this just becomes 1 over T2 minus 1 over T1. These two are equivalent. Okay, the only difference is here in the equation on the top, it's 1 over T1 minus 1 over T2, and then the equation on the bottom, it's 1 over T2 minus 1 over T1. The only difference is a negative sign that's in front of everything. Okay, so these are very simple types of calculations. Okay, so a very involved calculation may be that, you might be asked to get, you might actually be asked to compute K equilibrium at T1. Okay, so that in itself would involve a few steps that, as we just saw through the discussion earlier in this lecture and through last lecture. And once you have K equilibrium, you may be asked to find delta H superscript 0 reaction, right? That might be another involved set of calculations because now you have to look up entropies of formation. You might be given them, et cetera, et cetera. Once you have that, then you can go and proceed to find K equilibrium at T2, assuming that delta H is constant, or you're looking at a very small temperature range over which you can say that delta H is constant. Okay, so in this expression, in these two equivalent expressions, is a lot of stuff they're loaded with a lot of stuff. Okay, and this form, these two forms are a specific case where we have weak dependence on temperature. The general form is here. Okay, and of course you don't need to memorize this, but you should be able to know the difference in terms of when to apply the general form and when to apply a more specific form. Okay, so never memorize, always know the general form and then figure out what we did to get to a specific form. Okay, so that's the temperature dependence. Any questions on that? No questions? No questions at all?
It's not about this, but I was wondering if it's possible that you can allow us to go back and check or practice our problems from homework number chapter 4 or 5, I think it is.
Yeah, okay, yeah. I did that for the first term. Did that work?
Yeah, it was pretty helpful.
Okay, all right. Yeah, sure, I can do that. Yeah, thanks for reminding me, Sheldon.
Thank you.
My pleasure. Yeah, I didn't realize that. Okay. Any other questions?
Actually, I have a question too.
Sure.
Are the contents of homework 6 going to be on the exam?
I believe that was some kinetics. Am I correct?
I think.
Yeah. So, if you have to compute, yeah, they would be.
Okay.
Yeah. Anything with kinetics, I would, those problems, as I recall, were fairly straightforward. And I think they do include computing Ks or temperature dependence. So, if you were able to do that, you should be confident. But, I really want you all to sort of take away some of the conceptual parts of this course. I know, a lot of you like to apply it, but I think as I found in my 51 years on this planet, starting at your age, is when I understood the concepts that underlie a lot of these things, I was able to then, when I had to apply some of these things, I knew when things didn't work and why they didn't work, and I didn't really have to then go back and relearn everything, because when I was your age and sitting in class, I would actually try to understand what it was that was behind the machinery or under the hood, because it can be painful when you're applying something, not knowing what's underneath and what's going behind it, and you can bang your head against the wall. But if you actually understand some of the concepts and the fundamentals behind it, if you run into a problem, then you can automatically say, oh yeah, well, I assume this, or well, of course this is not going to work because this assumption probably doesn't fit. And so from this course, I really hope that that's a habit that you learn, because that's the habit that will stick with you all your life. Whether you remember K equilibrium and its temperature dependence, you may forget it, in a week or a month, but I hope that you will take the habit to sort of look under the hood in whatever you do. And if you learn that from this course, I think that's success. Okay. Anyway, I talk too much. Okay. Any other questions? Okay, I'm going to stop there. I will do a sort of an example, kind of a problem next lecture. Very simple. You put the homeworks. I think I picked them because they're also very sample problem-y. Okay, so and I think I'll end there. Any question? And I wish you all a good week. There seems to be another warm week in Newark. It's great. Enjoy. Okay, I'm done.
Thank you.
Okay.
Thank you.
That's it.
Thank you.
Hey, Professor. Oh, sorry, someone else was talking. Oh, no.
Go ahead.
You were saying about having a camera on for the exam on Thursday.
Yes.
And I've had computer issues for the past couple semesters, and I've never been able to make my computer camera work. Would it be all right if I set it up with my phone and taped it to where my computer camera would be, and then use that?
Just be there. Okay.
Okay, because I can definitely be here and I can make my audio work.
Okay.
But honestly, I have to call in with my phone to make that happen. But yeah,
Okay.
I'm on my phone right now, so you probably see me in here twice.
Oh, I see.
Yeah, I'm on my computer, and then I had to call in to be able to talk. It's my computers. I've had a lot of issues with the mic, and the cameras still have never worked.
Okay. Well, just try to be here and join us.
Yeah, I can definitely be in the Zoom session for any questions or anything.
Okay. This is just something that's gonna, I don't want to. I hate being a meanie, but for 444, I'm not sure if you're gonna be planning to take it, but there's 4 instructors, so this might be an issue again. So just giving you a heads up.
Yeah.
Okay. I mean, if you're in my section, then it'll be fine. But just a heads up.
Yeah. All right. Sounds good.
Okay. Yeah. Thanks for letting me know.
All right. No problem. I just wanted to ask real quick.
Okay. Thank you.
All right. Thank you. Have a good one.
Be good. Yeah. Be well.